the record button and present slideshow. So welcome everyone to this math reading group on functional data analysis. It's something I've played a little bit with, and I had a course on it when I was in masters. It's pretty fun, and I thought we had a few of these reading groups on funny types of data. So I figured it would be nice to cover functional data too. But before we start, today is the 25th of August, which is the anniversary of the death of Friedrich Nietzsche in 1900. More interestingly, it's also the anniversary of the first announcement of Linux. So Linus Torvalds made the first announcement in August 1991, and I think in 17th of September the first version of Linux came out. And finally, it's also the anniversary of the Voyager 1 probe exiting the solar system. So many interesting things seem to happen on the 25th of August. There's a bunch of them on the Wikipedia page. But to give maybe another motivation of why I wanted to give a session on FDA is that there's a series of paper and a series of ideas in machine learning where your function is a data. More most obviously from this series of paper going from data to functa, which honestly I hate the word functa. It's ugly. I hate it. But anyway, I see that they have the point that really most of our data points, we're treating them as high-dimensional multivariate data, whereas really it's a function. It's a set of values defined on some domain. And in their paper here, they're modeling, use neural networks to fit these functions. That's not quite what we're going to do today, but it's still the idea that really your function, your data has more structure than simply being multivariate. It's a function defined on some domain, and sometimes depending on the properties of that domain, you can do a lot of stuff. So to give a brief outline, so I'll spend quite a bunch of time on functional data itself. So how to get it, how to approximate it, and so on. Then some basic functional statistics. So because we were doing statistics in function spaces, we want to be able to do stuff take the average of a variable, take the covariance, stuff like that. So we'll see about that. And then we'll finish with some pretty cool stuff involving functional PCA. So you extend the notion of principal component analysis, but in this functional setting, and also do some kind of linear regression. So let's keep going. Let me keep the chat in view, so if you have any questions. I have a brief note on software. So quite sadly, most of the people working on functional data analysis are actual statisticians, which means that most of the software they write for doing functional data analysis is in R. I was able, however, to find one Python package for functional data analysis that had quite a lot of features. Probably not nearly as much as the R ones, but I figured probably better for this crowd to use Python instead of R. So if you want to play with it, check these links out. So so what is functional data? So as mentioned, in many applications, in many data sets, really the data can better be described as a function of some domain T. So you have some domain T, which usually is going to be nice enough, not infinite, not super big. From that domain to, let's say, R or RD. So some domain might be pretty funky to just a vector space. So and specifically we speak about continuous domains. So let's say I have an interval or a manifold or stuff like that. So examples, maybe the most common ones and the most common in applications in FDA is time series. So I have a one-dimensional interval that represents time, and let's say goes over S. So let's say you're tracking stock values or NVIDIA stocks, for example. That's a perfect example of a time series, and it's one of the biggest applications because it's easy to model using FDA tools. But you don't necessarily need to have a time dimension. You can just have a spatial data. Let's say I have a data set of temperature at every point on Earth or like sensors. But then, of course, these sensors will be measuring over time, so they have both time and space as my like input dimensions. I can also treat images as data, right? An image is like can be seen as a function that returns. Let's say my image is like a square. It's just a function that takes a point on the square and returns a color, which is like three numbers. Another example which might be a bit surprising, but if you do anything with like ODEs or PDEs, well, actually you're already manipulating functions, and like in PDEs especially, you're doing like differential equations in a functional space, so it's natural to play with these tools. But even as ODEs, when you solve an ODE numerically, a lot of the numerical solvers will output not just like points where it has stepped, but like it will be able to give you like a nice smooth curve that like extrapolate or it's close to the actual solution. So that is a nice case where you almost immediately have your function, which is not usually the case. So example of functional data, and I have a bunch of examples here. So like these on the right are from the Python package, and they're like very common data sets people use in FDA. So on the top, it's like the height of a bunch of children, like boys and girls, measured over the lifetime up until 18 years old. See like okay, what are the differences in like growth patterns? Do they have growth spurts or difference between boys and girls and so on? Bottom one is another common data set. It's just like they took 20 people and asked them to write FDA in one stroke, and okay, that's a curve, and that's your data set. On the left, it's like maybe the data set that like inspired me to do something on FDA. You may have actually seen it last year. Like last year, we had like a growth, like unprecedentedly high ocean temperatures, which caused a bunch of problems. And there's like this nice website. I forgot to put the source on the bottom, but there's this nice website that gives you these curves, and there's like these curves are a bit complicated because they're like the output of a complicated climate simulation that takes as input the like sensor data. So it's like highly processed data to give you like the average ocean sea surface temperature for each day for like over 40 years. So like I think they go from like 1981 to this year, and so like this topmost curve, blue curve, is like 2023, where we had like really high temperatures, and then this partial red curve is like this year, 2024. Uh, that might not be completely up to date, but roughly that's what it looks like. Okay, so let's be formal. So a random element x, so a random variable, is a functional variable if it takes value in a function space. And we're going to denote that as a set of the xt for t over the domain. Depending on the application or the domain, you might have domains in the field. You might see x underscore t, very common in like time series analysis and stochastic processes. And we're going to distinguish the random variable x written in capital from a realization, so an observation, with small x. So this is like the random variable. It has like a distribution, maybe, and this is like a single sample. If you want examples of like common function spaces, a simple one would be like the continuous functions from 0 to 1, or like any interval you might like. So continuous functions are very nice function space. Depends on what you do. Another common one, which you don't want to like too much exactly what it is. It's L2, so the set of functions from 0, 1 to r that are square integrable. So like this integral is smaller than infinity. And this is a function space. It has nice normals and stuff. And depending on your problem, like there's a bunch of these different spaces that you can play with. Now, okay, this is all well and good, but usually we can't really observe like infinite amounts of data to get a nice function. Instead, we observe like only the function at like discrete points. So let's say I'm measuring the temperature like at a few weather stations. I can do that like maybe once every day, and that's it. That's like once every day I get a sample from each of my stations coming in, and I put them in a data set. And so we have the problem that we need to like find a way to, from these finite samples, get a function representation. That's one of the big challenges in functional data, and that's what we'll be talking about for a while. And there's more problems than that. Because I mentioned, okay, my weather station, maybe they make a measurement every day and they send it. Okay, that's nice because every day I get a measurement. That would be like densely sampled, regularly sampled data. Cool. Unfortunately, I don't always have like densely or regularly sampled data. Maybe my data is not sampled at like equals interval of time. Maybe okay, I get a measurement when I get one, and or maybe I skip one, maybe I lose. Like let's say I take measurements of my electricity counter every week, but I'm a bit uh, not super rigorous about it. Maybe I forget or whatever. So my data is then not sampled equally, and maybe like a couple of weeks I forget. Um, let's say I have multiple people gathering uh, electricity counters, and I have another problem which is that they probably won't be recording their data, making the measurements at the same time. So now we also have to deal with that my different like data streams are not sampled at the same point. And on top of that, of course, it might be noisy. Maybe there's like uh, error measurements in like my instruments, or maybe like someone like can't read the counter quite well and makes a mistake. So we have to deal with all of these. So okay, before we actually like go into the functional data, it's a good question to ask. Okay, why not just use multivariate data? It's right. It's just a stream of data, so we could assume okay, this is just a single observation of a really high dimensional multivariate observation. This is not a good idea, and the reason why is that one, it only really works with densely regularly sampled data. If I don't have like nice densely regularly sampled data, there's very little that I can do to like use these different observations of each other, or whatever things I might do are like functional FDA with extra steps. So we might as well. The other one is that like if you look at this, right? If I look at the temperature at the like t and the temperature at day t plus one, they're going to be very close. And so that means they're going to be highly correlated. And usually when we do like statistics, we want to avoid having too many highly correlated observations. So if we can avoid that, it would be nice. And then finally, another thing that we can do with functional data that we cannot really or nicely do in the multivariate case is that if we have like sufficiently nice functions representation, let's say I represent my data as like differentiable functions, then I can now take the derivative of my observations, which I can sort of do with like my noisy data or my just direct data, but it's not going to be super nice and it's going to be very noisy, and like it's much better and much easier to work with functions for this. So we might as well. So I think, right. So let's say I have a bunch of samples and I want to find a curve x such that y of t is x of t plus epsilon of t. And epsilon, so x is like what I really want, it's my actual data, and then epsilon would be measurement noise. And the generic framework for that, if you have like your favorite parametric family of functions, is that like approximate it with your family, and so minimize. Okay, I'll answer that question in a bit. So just like you would do with a neural network, just minimize over the parameter space theta the distance between your parametric function x of theta and your data y. So you're asking what did I say about highly correlated data? So I mentioned that because if I look at like this example, the temperature at T is very close usually to the temperature of T plus 1 because I assume that my data is continuous. And so that means that like temperature at T and temperature at T plus 1 across all these variables is going to be highly correlated. They're going to be very close to each other. And so if I just take each of these as like one highly high dimensional multivariate data sample, I have quite a lot of very correlated or extremely correlated in some cases variables, which I would prefer to avoid. Does that answer your question? So yeah, in general, pick your like function approximation scheme and fit your data with it. Um, Ideally though, we'd like the parameterization to be easy to manipulate. And easy means here, for example, we'd like a vector space, like the representation of our functions would be just a vector. That's what we'd like it ideally, and the reason for that is because we want to use these like traditional vector space statistics that we know. And for example, neural networks are not a great fit for that because, okay, if I have two neural networks, how do I take the sum of them? It's not simply the sum of their weights. I can't just like sum each like data matrix or layer matrix with one. That's not going to work. So that's what I mean by like a nice, easy representation in this case. Okay, so we want like linear, so we're going to use a very general approach called the basis function approach. And the idea is that if you have a function space f with a norm, so that's a general thing in like in functional analysis, you always have some kind of norm or some kind of at least some kind of topology, but usually some kind of norm on your functional space. And the reason for that is that there's a lot of things that won't make sense if you don't have it, so it's preferable to have one. So if I have a function space with a norm and I have a set phi k, a subset of f, it's going to be called the basis of f if it is linearly independent, so I cannot like express any one of these phi k using the other ones using linear combinations, such that for any other functions in my space, I can find constants c of k, and maybe I can like truncate my we only want up to big K functions, so maybe they depend on big K too, such that so if I take f minus this linear combinations of my basis functions, as I increase the number of basis functions that I use, it goes to 0. So what this means really is that I can get as close as I want to f using a finite number of basis functions. That's what this means. And so when we have something like this, it's called a basis. Note that not every vector space has a basis like that. So when you have one, it's pretty nice. And honestly, the common ones have a basis, so we don't even need to worry. But that's a note. So that's a general framework we're going to like pick a basis and use that to approximate all other functions. And so an easy example, for example, if I take continuous functions as my space with this norm, so norm f infinity, also called the absolute norm. In a sense, like this norm means that if two functions are close, like the difference between any 2 points of these functions are like bounded by some epsilon. And so in continuous functions, monomials or polynomials in general, but monomials tx to the power of k are a basis. But they're not great. Like numerically, they're horrible, so we never use them. A better approach, which is like stabler, it's called Bernstein polynomials, and they're defined as like this ugly expression where you have a binomial coefficient here and then t to the power of k times 1 minus t to the power of k minus k. So if you want to like fit functions, polynomials, generally this is the better options. But again, for very large k, it's numerically unstable because we have this binomial coefficient that grows and grows. But it's still a fairly like good option if you have nothing else. A more common one, which actually is the also common in like deep learning and stuff. If we have a space of L2, so square integral functions, with obviously the L2 norm, then the Fourier basis of so the first function is just constant 1, and the other one is just like cosine of 2k p, so 2k pi times t, and sinus of 2 pi k times t, so alternating, so just trigonometric functions of increasing frequency. Um, so these functions, they form an orthonormal basis of L2, which is really nice because orthonormal, which is also really easy to like use this basis like and compute the coefficients. And in fact, if you have regularly sampled data, then we can actually fit with this basis using FFT, which is really fast. Like normally, you it would be like a linear solve, a least squares problem to compute the coefficients. So more like O(n) squared, but using FFT, it's n log n. So if speed is like a concern for you, the Fourier basis is usually pretty nice. And of course, there's like other like families of orthonormal functions depending on like your actual space, but there's stuff like orthonormal polynomials, so like Chebyshev, Lagrange, Hermite. So like depending on your applications, you can use them, and like there's already highly optimized software to compute expansions in these bases. Okay, but so these are like very common at least in machine learning, but we're going to move on to another one called B-splines, and the B stands for Bézier, which if you ever used like an image manipulation software or anything like that, you might remember the curves tool, right, where you can manipulate. That's a Bézier curve. And the idea of those is that we're going to use a spline, so a local approximation over an intervals, so here using polynomials. And the reason this is nice is that even though it's not an orthonormal basis like the Fourier basis, we have a bunch of knobs to control this spaces. So first of all, let's say I'm like approximating over the interval 0 to 1. I can choose my number of basis functions, which is going to like tweak the number of intervals I have. And then I can also tweak the degree of polynomials I can use as my basis. And then, for example, like this is using d is equal to 2, which is going to give me up to linear functions. And so in this case, actually, you can see my first function, it's 1 here, and then linearly goes to 0 at the next one. The second function goes from 0 to 1 linearly as well. So actually, like these would be doing just linear interpolation, right? Because it says, like if I do like a times this first function plus b times the second function, the value of my function a p is going to be like 1 minus t times a plus t times a times b. And so I'm just linearly interpolating. And then if I increase the order, I'm still doing some kind of interpolation, but over like a higher degree. But that's more if you're interested, you can look up like Bézier functions, whatever. The point is that using these pieces of functions, I get like a nice basis that's reasonably easy to approximate. They have some nice structure. And importantly, I can tweak. I can tweak the number of like the number of intervals, and I can tweak the degree. So if let's say I absolutely want my data to be like differentiable up to order k, then I can crank up the number k so that the degree is high enough. So like on the right here I have just using I think quadratic functions. So each piece is like you can see this piece here is just a parabola, this piece is a parabola, this piece is a parabola. But because it's doing that piecewise and making sure that the derivatives and so on match between the intervals, I can have some very complicated functions. And so using these, it's quite flexible and you can like tweak it very easily to get a pretty good approximation. So to fit splines and really most function basis, what you do is solve a least square problem. So you want to fit the theta y to minimize the sum of square residuals um, over my sampling points. This is just, again, a least squares problem. I can construct my matrix of evaluating my basis functions at the sampling times, pull a vector, and then I find my coefficient by solving this linear problem on the bottom. And so, depending on the basis, I might be able to solve this linear problem very efficiently. And once I am solving it, again, there's like plenty of high quality software for that, so it's an easy step. And so an example, okay, so here's the link. So we have the data, the raw data on the left here again. Then now I have a bit of a problem because this red curve, I don't have all the data. So I'm going to remove it from my dataset for the purpose of smoothing. And actually, even the first here is also incomplete. It only starts after January. So I'm removing like 2 data points, but that's not a problem. The rest of them I'm going to fit using a spline basis functions. Here I think I have like about 20 functions in total, and you can see that I have a good like smoothing of my data. As a side effect of that, my fitted data is much smoother than I can see in the data. So like these the high frequency oscillations, which I've decided or asserted that these are just noise or I don't really care, so I've smoothed them out. This like you want to do this depending on your application, of course. But in this case, I assume, okay, this is just noise, I don't care about it, I want smooth data, let's roll. And so this is my smooth data. I've also plotted in black the average of all my data, which I can do that easily. And notice that, right, because the average at like the end of the year is going to be very close to the average. At the beginning of the year, I can consider this mean function as like periodic. So in a sense, the periodic pattern in like sea level temperatures or sea temperatures is completely captured by the mean function. But we'll see more about like the notion of mean functions later. Okay, so far so good. Also note that as a side effect, I'm describing my data using many fewer numbers than using all the data points. So it's also like a dimensionality reduction tool. Okay, another example. So back to like this height of children dataset. I've already smoothed it, and then I've taken the derivative of it. So I've smoothed it using again B-splines, and then taking the derivative gives me, okay, you might need some like um, adjustments to say, okay, is this like real data, a real pattern in my data, or just noise? But maybe, okay, it looks like, okay, they started growing quite a lot, and then maybe some of them like growth spurts, whatever. So this is pretty cool. Okay, so enough with functional data. Note that I'm skipped a bunch of things, like sometimes you might want to apply some smoothness or like penalty on your data, or there's other transforms you might want to do. I'll leave that to further read. So on to functional statistics. So before we actually move on, I mean, this slide might be a bit insulting considering like what we've talked about before, but just in case. So in general, we prefer to work in a Hilbert space, which is just a vector space of functions. So you normally a vector space, that's fine, with an inner product. So I can take dot products between vectors or functions, and the inner product has to satisfy that it's commutative, real valued in this case. It's bilinear, so it's linear in the first argument, and then because it's commutative, it's also linear in the second argument. And then it's also positive definite, which means if I take the inner product of x with itself, it's greater than 0, and if it is equal to 0, then x must be equal to 0. And these properties mean that the inner product defines a norm on my space, and so now I have a nice norm to do analysis with. Now, the Hilbert in Hilbert space means that it's also complete, which is a topological condition. It's a technical condition. It just means that I can take limits in most reasonable cases. So if you don't know like what Cauchy sequence means, don't worry. It is a technical condition which is usually verified in most cases. And if it's not, then run away. Um, okay, so we want to generalize the notion of like sample and population mean and covariance matrix in infinite dimensions. So it's nice to like recall what those are in finite dimensions. So assume I have like some IID variables in RD, then I can take the sample mean, simply 1 over n times the sum of the xk. That's the sample mean, and it's famously an estimator for the actual population mean, so the expectation of x1. Here it's x1, but it's any of the x's because they are all identically distributed. I can also take the covariance matrix, the sample covariance matrix, as this more complicated object, but again it gives me a matrix, and it is an estimator for the population covariance, which is the expectation of this quantity. Can we generalize this to functional variables? Answer is yes, but there's a couple of not so nice mathematical details, a few of which I'm going to be skipping over. But I'll still give some like details. So the definition of like the expectation for a functional variable is using this notion of weak integrability. So a random function is weakly integrable if I can find some function mu in H, such that the expectation of this inner product, note that here this inner product is just a scalar valued um, random variable, so I can take the expectation of a scalar value, or of a scalar. So if the expectation of x times y is simply the inner product mu times y for all y in H. So if I can find a mu like this, then it's called the expectation of x. So mu is like expectation of x. Then I can add another condition. So x is going to be said to be integrable, noted as x in L1 of H, if the expectation of the norm of x is smaller than infinity, which is similar to the technical conditions on like random variables, like scalar random variables having finite first moment. It's the same idea. Now we have a nice little lemma. If x is integrable, then it is weakly integrable. So if this is true, then this is true. And also, if my x is weakly integrable, so I have mu, then mu is unique. There's only one of them. So that's nice. That means if I'm weakly integrable, I for sure have an expectation, and it is unique. There's only one. And so a common example, if I'm working with L2, then the expectation of x evaluated t is simply to be the expectation of x of t. And notice the gray for almost everywhere. It's a technical detail that we will be freely ignoring here. For intents purposes, assume that it's you take the expectation pointwise and that's it. Okay, that was okay. The covariance operator is a bit covariance is a bit more tricky. Suppose now that um, I have x which has finite second moments. So the expectation of the norm squared of x is well defined. Then I don't have a matrix anymore, but I have a linear operator C from H to H, and it's defined as acting like this. So C applied to Y is going to be the expectation of this inner product x minus the expectation of x with Y times the vector x minus the expectation of x. So this is between, and it's called a covariance operator of x. And if you're a bit troubled by this, we can look at it like at this definition in infinite dimensions. For here C of y, I can sort of move things around, right? This inner product, it's simply x minus expectation of x prime prime with y, and because scalar I can move it around, so I can move this here, and then y is constant, so we can factor it out, and so it's again the expectation of this thing here, which we know is the actual covariance matrix, and so it's simply the covariance matrix times y. So it does in fact match like the covariance infinite dimension. So okay, it's a covariance. What can we do with it? So the nice thing is that if we are working with R2, and suppose for easiest case that the expectation of x is 0, then the covariance operator is going to be a kernel operator with kernel ct of s being the expectation of x of c times x of s. And kernel means it's an integral operator. So it looks like this. C applied to y evaluated t is simply going to be like an integral from 0 to 1 of c of ts times y of s ds. And you can sort of like, if you squint a bit, this looks like a matrix multiplication. Like because like the integral is like a continuous sum, and then like have this c of t which is like a matrix times my vector ys. It's like a generalization of a matrix, but with integrals and continuous functions instead. So the fact that this is true is actually pretty nice. The reason is that one, so CTS is like the cross covariance between any two, all the cross covariances of my data of X, it's going to be symmetric. And the nice thing about that is that that means that the operator C is symmetric. So that means that the inner product of C times, so inner product of Cx with y is going to be the inner product as x with cy. So it's a symmetric operator. It is also positive semi-definite. So cy with y inner product is greater than 0 for all y. Again, really nice. And finally, that's more to do with the fact that we have a kernel operator. C is what's known as a compact operator. And we don't need to go into details about what a compact operator is, but all of these mean quite a lot of really nice things. So for example, symmetric means that we have only real eigenvalues. Positive means they're also real and positive, and compact means except maybe 0, we only have eigenvalues. And so like basically compact operators like this, like symmetric compact operators are just about the nicest operators you might hope to find. So it's actually a pretty good news that this is the case here. So like if you are functional analysis, this is how you'll react to these. Like this is already pretty interesting, and these are already these like make it even better. So like these properties will turn out to be very important later on. Okay, so before moving on to actual applications, I mentioned like a nice generalization of classic statistics theorems. So notably the like central limit theorem and the law of large numbers. So let's say I have an ID sequence of random variables xk in Rd with finite moments, or at least, okay, this is a bit wrong, but it's fine. So it should be the expectation of norm of xk is more than 1, so they all have finite uh, finite expectation. Then the sample mean converges to the population mean as the sample size increases. That's the law of large numbers. And if also their second moment is well defined, then the this random variable here, so xk minus the expectation, is going to converge in distribution to a normal distribution with covariance being given by the covariance of x1. So that's more the uh, central limit theorem, right? The x minus its mean in like as I take an increasingly large sample, it's just to be a normal distribution. That's the like multivariate case, and it turns out that we basically have the same thing in functional setting. So here now let's assume I have an NID sequence of values in a Hilbert space H such that they're integrable, so in L1 of H. Then, so first of all, I have to be a bit more careful, but it's essentially the same. My sample mean converges to my population. And again, like ignore the almost surely or separable if you don't know what those mean. And again, if so, the law of large numbers holds again in the functional setting. And then if I also have finite second moments, then I also have a version of the central limit theorem, which is a bit different, but it still means that the like x minus the average, not the average, x minus x expectation in distribution is going to be closer and closer to some like infinite dimensional Gaussian distribution, which here is called a Gaussian element. So it's basically a random functional variable that is only completely characterized by its mean and its covariance. And I'm fairly certain that that would be a Gaussian process, but I'm not entirely convinced that it's exactly the same, depending on your functional space. But you can just think of it as like, yeah, a Gaussian distribution, but infinite dimensions. Cool. So these are pretty nice. We won't be proving them, but it's good to know. Okay, so enough with the like not so nice math, of which I skipped quite a lot. Let's move on to like the maybe the closest things to the application, so functional PCA and functional regression. So as a like brief recap in finite dimensions, uh, I can use the fact that my covariance matrix is a symmetric positive matrix, positive semi-definite, sorry, which means that it has positive eigenvalues and often normal eigenvectors to like decompose my data. And so, for example, if I take the inner products with my so eigenvectors vi, those give me something called the principal component scores. And if I express my this is correct. So if I express like my data using my basis and maybe truncate it, um, this is basically like a dimensional reduction operation, right? I can reduce the dimensionality of my data, and the particularity of using this is that it also maximizes variance. So like the taking the k first principal components maximizes the variance of my data that I am capturing using only k dimensions. So it's in some ways like the optimal way to reduce your data using just a linear transform, and yeah, that's why it's so useful, because it like quickly tells you, okay, this is like the most important dimension, this is the second most, this is the third most, and so on. So that's so finite dimensions. We do the same in infinite dimensions. So again, suppose I have an Hilbert space, and suppose I have a function, random variable with finite second moments, and assume that the first moment the expectation is 0, otherwise we can center it, so it's like no big deal. Suppose that my covariance operator has eigenvalues and eigenfunctions, which, remember, like I mentioned the thing about comparators, right? It's usually the case. Then I can again define my functional score, my like functional principal component scores, as simply the inner product of x with the ith eigenfunction, and then vi here is just going to be the ith principal component. So again, I get a ranking of this is the most important direction my data has, is the second most, and we'll have another bonus, and we'll see an example that usually these are quite interpretable. Usually interpretable even in the multivariate case. Here it's going to be even better. One note is that in practice, of course, we only have the sample covariance, so we cannot estimate all of the eigenpairs or eigenfunctions. We can only do that up to n. But to give an example, so here I have again my sea temperature data, and I've like computed the FPC of it using for only the first four principal components. Um, in order, the first is this blue one, the second is this yellow one, I think red is number 3 and green number 4. And actually, if you look at like the scores, the most important one is the blue one, and then the yellow one, the orange one is a little bit, and then the other two are like basically noise. So really, it's like the first two that are the really important ones, and we can actually interpret them. So remember, we remove the mean from this set, so we have the mean here, which is like the PRD component in the temperature data, and then we have like this blue, which is basically constant. So in a sense, the blue, the first principal component is just like the average temperature of that year. It's like it shifts. So it's like if I increase the score for this blue curve, I basically shift my curve up. And then the second one, we'll see exactly what it does later. But it's interesting to look at the scores. So as I mentioned, the blue one is like the average temperature, and we can see here that actually um, it basically steadily increases over the year. So oops. Um, and then we can see that the other like scores are fairly close to 0. Like the yellow one is a bit larger, but the other one are basically just noise. And if we look at what it does, so as mentioned, the first component just like shifts the curve up, and the second one, right, because it's like it like goes from negative to positive to negative, it's basically like a balancing thing. So it's like balances out the temperature differences between the first and the second half of the year. And yeah, third and fourth one are much less interpretable. So much to say, like these two are the most interpretable. And that's usually the case, like when you do FPC on like temporal or like this kind of data, that you find like nice interpretable PCA components. Here in this case we have like a nice illustration of like, yes, indeed, the average temperature is increasing. But anyway, so I'll talk very briefly about functional regression. The reason for that is that it's like another entire can of worms, and like we spent enough time already. So, but let's give the basics. So we want to do simple data analysis using functional data, and one of the most like basic type of functional or of data analysis is linear regression and variance, like logistic regression and so on. So it's nice to like know these basic operations so that we can like fit them into other methods. And here we have like different flavors depending on what exactly you're trying to model. Like if I'm trying to model a function using scalar variables, then in the first case it's fairly easy. It's just okay. Let's say y for like some index k and g would be my like variable g is like the mean plus like the effect of variable g plus some noise. So like it's function using scalar variables. I can do the inverse. I can try to model a scalar variable using a function. And in this case, for example, in L2 would be something like this. So y could be like a constant alpha plus the integral of x times a function b of t, beta of t, plus some noise epsilon, and then b of t is the function I'm trying to learn here. And there's like a bunch of schemes to learn it. It's a bit complicated. And then I can also do like trying to learn fit a function using other functions. And so this is a even more general case than trying to learn a function alpha t and like a kernel beta t of s. And of course, then like I have multiple variables of different types and so on, but that's generic. Note that here I'm using integrals assuming and working val 2. In general, this would be just an inner product, so inner product of x with b, with beta, and this would be okay, an operator applied to x, and so on. So that's functional regression. Uh, I just have just one example, and then we move on. So remember we had like this data for 2024, which was incomplete, and let's say we want to like predict what's going to happen next. And to do that, we're going to use the PCA components that we computed earlier. And so basically trying to fit my partially observed data using my PCA components. Now, I have a problem with that because I only have the data up to some time t. Well, I don't know what's after that, so like I have to adjust my loss function. But let's say I'm defining a new space where my norm is just integrating up to my sample time m. So I'm only integrating there. Then I can still frame my problem as trying to minimize the norm between x minus the average minus some linear combinations of my PCA components. And so this is what I've done here. I cheated a bit because I could not find a way to like to do this exact problem like functionally in like the Python library. So what I did was just evaluate x, mu, and phi at like my at all these days and do a least square like finite dimensional least squares on that. And that gave me this. So interestingly, it predicts that we should see the temperature dip like fairly soon. Keep in mind that it's probably not going to happen like this. Like I think what happened here is that because I mostly have like the first half of the year, it predicted a high like average temperature, and then the second component is like so the skewing this second half quite a lot. But it's going to be interesting to see if this holds up. Okay, so before we finish, so beyond linear models and stuff, of course, there's like a bunch of other machine learning techniques we can do with functional data. So because we have a vector space representation, it's nice and easy to manipulate. we can use the basis coefficients as vector features in a neural network and just let it rip. That's quite well. And for example, there's a nice structure of like neural operators and especially Fourier neural operators, which do exactly that. So like these are like a specific network architecture for PDEs, and as part of their architecture, they take the data, transform it in the Fourier basis, and do some operations like apply some layers to the Fourier features. So it's exactly this like functional data approach here. Other stuff we can do it because we have metric space, right? We have a norm. We can do stuff like KNN, K-means, and so on. Like you only need that basic structure and it works. Um, do note that in general, however, if you want to do like other FDA techniques like this stuff in a neural network, it's not going to be so nice because basically these FDA techniques like computing integrals and so on is not especially GPU friendly. At least as far as I know, there's very little GPU implementations for this stuff, and even like if you had, like it wouldn't be especially efficient. So something bitter peel, you need something that efficiently uses your compute. So I don't expect that you'll see a lot of like high level functional data technique in deep learning, but at least as a like an input feature, I think either like using the basis function representation or FPCA as like a nice condensed feature, probably going to like be useful for a bunch of problems. Obviously not in every problem, but worth trying, I think. And yeah, I think we've reached a conclusion. So yeah, we can do statistics in infinite dimensions. It's a bit versatile. We can like reduce dimensionality and like do that on a bunch of like types of data. The one problem we have though, if we have like an increasing domain dimension, if I have domain like a volume or like yeah volume over time, we run into again the cursor dimensionality. Fitting like these splines over high dimensional domains gets more and more expensive as the dimension increases. But still, we can do quite a lot of things we know from finite dimensions, in particular PCA, which here works super well. So yeah, that was it. I have like a notebook with like that I've used to generate these plots. I'll upload it after cleaning it up, but yeah, it's a bit fun, quite fun to play with this. So yeah, does anyone have questions? Okay, so no questions. I guess not. That's fine. Um, Thank you. What is the point of this? So the point of functional data analysis, you mean? While you're writing, so I'm going to assume that you mean what is the point of doing FDA, and the point, at least the first point, is that really in a lot of cases, a lot of cases, it makes sense to see your data as a function, and when you add some other assumptions such as okay, it's a continuous function or it's a differentiable function, then it makes sense to use another representation than just your bare data that lets you use these assumptions like it is continuous, it is differentiable, and exploit these assumptions as features. More practically, it's a dimensionally reduction technique, which is quite flexible. Um, I see you've stopped writing, but to answer the other question, so could I reiterate on when you would want to use FDA as opposed to other traditional ML methods? So obviously FDA it's much more statistics. So it's mostly statisticians or data analysts that might want to use this, much less in ML, but really anytime, like you could think of it as, okay, I have data that is like time series or makes sense to see as a function that is continuous. If your data can be interpreted this way, you probably have stuff to win by doing a FDA approach at least as a data transform. Because now you have a representation of your data that's a bit nicer. Maybe because you've thrown out some noise and maybe you might not want to throw some noise, but still. And so, so also to go back to the beginning, right? So we remember we can have all these problems. Suppose that your data is like, I don't know, sparsely sampled data. Like I have this problem. Like I do like try to record every week my electrical counter, but I don't do it every single time. And so if I want to visualize the data how to do statistics with it, it's much nicer to have like a smooth curve or like a slightly modified representation than just the bare representation. But about if your data can be interpreted as a continuous or otherwise function, it's usually a good idea. And for example, so I'll move on to the your question, Hawk. So I would say the like the nicest thing in FDA is like FPCA. Here I could like do PCA on the raw data. It would work. It would be more expensive because it's much more a lot more highly dimensional, and I still don't. I would not have the nice interpretation. Well, I would have, but in some sense, because I smoothed my data and because I've uh, simplified the problem, it's cheaper to compute and it's smoother. And here I can interpret these as actual functions and so on. It makes sense. I can do that on just the multivariate data, but it's noisier, it's larger, and so it's not as nice to work with both numerically and statistically. But tell me if that satisfies your question or not. So in some sense, isn't the network finding some reasonable basis? Uh, it depends on the context, I guess. Obviously, yeah, if you see a neural network as finding features as computing the features of your data, then yes, and then you might, but and then you might want to use that, like you might want to use that output basis, like the find output, the find is just a basis of features and try to do statistics with it, and that's where neural networks work really great, in that they can approximate some very complex functions on some complex domains. Here we have some specific assumptions on our data that you can exploit. And if you want to do statistics and like interpret your parameters and so on, do statistical tests, then it's better this way. Obviously, no one in machine learning does statistical tests, but not everyone actually does machine learning. There still are some like statisticians holding out, but yeah, I thought my sort of main motivation for it is to say, hey, this is cool. You could probably use it for in a neural network and have some fun stuff. But again, highly dependent on what on your actual data set. So yeah, I guess that was a bit rambly. Did I actually answer any of your questions? Okay, thanks. So great. So I think we can leave it at that. Mm, I again don't know when the next one is going to be. It's probably going to be on RWKV again to like finish up the SSM and so on. But I don't know yet when it's going to be, but it's going to be at some point. So yeah. So thanks everyone, and see you guys next time.